Magnetic field of electric current. Module 2. At the end of this module, you will be able to draw the magnetic field lines around a circular loop, draw the magnetic field lines around a solenoid, differentiate between a permanent magnet and an electromagnet, list the factors affecting strength of magnetic field around a circular loop, solenoid, and electromagnet. We know that when electric current is passed through a straight wire, a magnetic field is produced around it. It has been found that the magnetic effect of current increases if instead of using a straight wire, the wire is converted into a circular loop. So, let us discuss about magnetic field pattern due to a circular loop carrying current. When a current is passed through the circular loop of wire, a magnetic field is produced around it. The pattern of magnetic field lines are circular near the current carrying loop. As we move away from the wire, the concentric circles representing magnetic field lines becomes bigger. At the center of the circular loop, the magnetic field lines are straight. By applying right-hand thumb rule, it can be seen that each segment of circular loop carrying current produces magnetic field lines in the same direction within the loop. At the center of the circular loop, all the magnetic field lines are in the same direction and aid each other, due to which the strength of magnetic field increases. The magnitude of magnetic field produced by a current carrying circular loop at its center is directly proportional to the current passing through the circular loop and inversely proportional to the radius of the circular loop. Now let us discuss about magnetic field due to a solenoid. Do you know what is a solenoid? A solenoid is a long coil containing a large number of closed turns of insulated copper wire. Now, look at the figure of the solenoid. When an electric current is made to flow through it, then each turn of the coil behaves like a magnet. In this figure, current is flowing in the coil in clockwise direction. So, the left hand side of each turn of the coil act as south pole, whereas the right hand side of each turn of the coil act as north pole. In this figure, current is flowing in the anti-clockwise direction. So, the left hand side of each turn of the coil act as north pole, whereas the right side of each turn of the coil act as south pole. Thus, the situation becomes similar to a number of small bar magnets placed end to end with their opposite poles facing each other. That is, a solenoid is equal to a bar magnet. The magnetic field produced by a current carrying solenoid is similar to the magnetic field produced by a bar magnet. The magnetic field inside the solenoid are in the form of parallel straight lines. This indicates that the strength of magnetic field lines is the same at all the points inside the solenoid. The strength of magnetic field produced by a current carrying solenoid depends on the number of turns in the solenoid. Larger the number of turns in the solenoid, greater will be the magnetism produced. The second one, the strength of current in the solenoid. Larger the current passed through the solenoid, stronger will be the magnetic field produced. Third, the nature of core material used in making solenoid. The use of soft iron rod as core in a solenoid produces the strongest magnetism. An electric current can be used for making temporary magnets known as electromagnets. An electromagnet works on the magnetic effect of current. Let us discuss it in detail. We have just studied that when an electric current passed through a long coil called solenoid, magnetic field is produced. It has been found that if a soft iron rod called core is placed inside a solenoid, then the strength of magnetic field becomes very large because the iron core gets magnetized by induction. This combination of solenoid and a soft iron core is called an electromagnet. Thus, an electromagnet is a magnet consisting of a long coil of insulated copper wire wrapped around a soft iron core that is magnetized only when an electric current is passed through the coil. Factors affecting the strength of an electromagnet. The strength of an electromagnet depends on the number of turns in the coil, the current flowing in the coil, the length of air gap between its poles. That means if we reduce the length of air gap between the poles of an electromagnet, then its strength increases. Or if we increase the number of turns in the coil, the strength of electromagnet increases. Or if we increase the current in the coil, the strength of electromagnet increases. Now let us discuss about the differences between a permanent magnet and an electromagnet. Electromagnet is a temporary magnet as it exhibits magnetic force only when electric current flows through it. But a permanent magnet is permanent. That means its strength will be there every time. Then an electromagnet can produce a very strong magnetic force, but a permanent magnet produces comparatively much weaker magnetic force. An electromagnet can be changed. The strength of an electromagnet can be changed, but for permanent magnet, its strength cannot be changed. An electromagnet's polarity can be changed, but for a permanent magnet, its polarity cannot be changed. End of this module, you have learned that the magnetic field lines around a circular loop are circular in nature. The solenoid is a long coil containing a large number of closed turns of insulated copper wire which behaves like a magnet when an electric current passes through it. The strength of a solenoid or an electromagnet can be increased by increasing the number of turns or increasing the strength of current in the solenoid and the nature of core material used in making solenoid.